that they have. We will be working off of. Can someone confirm that they see my screen?
Yeah, we could see.
Right, we're good. Thank you, thank you. So we're gonna be working off this textbook. And does anyone have a specific thing that they want to go over?
Yeah, can we go over Hamming code?
Say that again?
Hamming code?
Hamming code. What the hell is that? Is that from like, hold on. Hamming code. Where is that from? I think Hamming code. From where are you guys learning Hamming code in 220?
Uh yeah, we just learned it towards the end of the semester.
2.43. Like for 1 second, let's see if we can find it. Although I feel like that specific thing won't be on, because that's more of a 240 type thing. I think it's, yeah, they're not gonna give you a Hamming code question. Control F. Well, it's not in text. That's
You know
not good.
what? Yeah, never mind. You're
But
right.
from because you don't really learn it
No, we
here.
don't learn it at all, actually.
Yeah, it's more of a 240 thing, if anything. Does anyone have any other topics they want to go over? Whoa, 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 whoa. Someone's saying Hamilton, you mean? Okay, okay, one at a time, 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 one at a time. So someone asked for recursion. We could do a bit of recursion. So recursion, Bayesian, 3.2. What's 3.2? Let's go in order. Algorithms. So induction, big O notation, Euler and Hamiltonian, currents, recurrence relation. Let's go in order then, if that's the case. What's the earliest? No one first. I'll go over where this recording will be posted. It'll be posted on the website, but I'll go over it at the end, the specifics of it. Algorithms. So let's start from algorithms because this is I'm just gonna go in order. So we're gonna go big O notation, then you don't need number theory. Then induction and recursion, and some counting, probability, then graphs and trees. Does that sound good? Gonna go in order of the. Everyone okay with that? So we're gonna start with big O notation. Then we're gonna go into induction and recursion, then some counting and a bit of probability, Bayesian theorem, relations, then graphs and trees, and then if anything else is needed. Everyone okay with that?
Yes.
Okay. All right. So growth of functions. Does anyone have a specific question that they want to go over, or do you just want to like go over the idea of the hell is this? Algorithms, growth of functions.
You
Growth
go
of
over the first few exercises like one.
on section 3.2.
Yeah.
Okay. Bubble sort. You won't need to know greedy algorithms. That's more 323. Growth of functions. Okay. Big O notation. So I'm assuming this should be a review for all of us, a lot of us here. Big O notation. If we want to bound a function, we say that f of x is big O of g of x. Well, if there are constants c and k such that f of x is less than or equal to c times g of x from all x greater than or equal to k. So let's just quickly do drawing for this. right? So if this is f of x, this is f of x, and we got g of x. So our constants are, so like this is some function constant times g of x, sorry. Right? So we say g is big O, no, f is big O of g if from a specific point. So in this case, that point is right here. This is our k, or in some notions they say x0. From this k onward, g times the constant is always going to be greater than f. And so you see there's always going to be a gap, right? So when it comes to choosing, a specific k and c, that's up to you. Usually we want to say the tighter the bound, the better, right? So we don't want to give like just a random bound. Like it's obvious that x squared is going to be big O of x to the 100th, right? But that doesn't really help us, right? We want to tighten the bound as much as we can. And then from there, we have other notions, such as, I think they don't do it, do they here? But I believe you've heard of big omega, big theta. Trying to find an example of those. We'll do a couple of those proofs later, but those different. Like you have big omega, big theta. You also have small o. We have these different bounds that also tell us information, right? And we have proofs, like prove something is big O of another function. Let's start doing some of those. Let's go to 3.2. 3 point, okay. Okay. All right. So which question would you guys like to do first? 1, 2, 7, 8. Okay, let's do a few proofs. Well, let's do one ordering them. Let's do number one first. Show you guys. So which of these functions is big O of x? So this is x is linear runtime, right? So for however many input, it's like a linear function. Okay, so which one is big O, i.e., which ones are going to be at some starting point onwards? It's always going to be less than or equal to x, right? So 10, this is going to be 1, right? Not, this is not going to be it, right? Because we have x squared, right? We could prove this is good. Log of x is also. And then this is going to be, that's good because you're always rounding it down. So that's always going to be less than or equal to x. And we have here, I believe that one's going to also be in it. Nope. X over 2. I think that's good. Should be. Right? It's just like quick showing, like determine which of these functions is big O of x. In general, for any polynomial, f of x, where the height we have equal to, let's say, x to the n, c, plus whatever comes afterwards, this is always going to be big O of x to the n. So you always take the highest power, right? So in this case, x squared plus x plus 1 cannot be big O of x, right? Because let's assume it is. That means we're saying that we could bound x squared by x. That means x squared is always going to be less than or equal to some constants times x. We could ignore that. We could ignore the x and plus 1. Doesn't really matter. But if we divide both times by x, we see that x is usually, this is saying x is less than or equal to c. But x is a variable. You can't bound a variable by constant. And you'll see, like, for a lot of these proofs, like prove f of x is big O of g of x, or prove that it isn't, right? If you get something like this is something we call proof by contradiction. Can't add that. Everyone okay? Just wanted to give that first question. FX. You guys want to do number 3?
Yeah.
Okay. So use the definition of f of x is big O of g of x to show that x to the fourth plus 9x cubed plus 4x plus 7 is big O of x to the fourth. Okay, so this is the strategy that I like to use. I learned this in data structures, but I like it. So we know that we want to prove that x to the fourth plus 9x cubed plus 4x plus 7 is big O of x to the fourth. Okay, so what I like to do is I like to take it term by term. So we know x to the fourth is less than or equal to x to the fourth, obviously. What's our x0? From x0 is, let's say 1. Okay. We also know 9x cubed is less than or equal to x to the fourth. From x0, well, we're going to say x0 is 9. Because 9 times 9 cubed, that's the same thing as 9 to the fourth. And 9 to the fourth is less than or equal to 9 to the fourth, which is good. Then we're going to say 4x is less than or equal to x to the fourth. Right, so like what you guys see I'm doing, I'm trying to break this into part by part. All right, so this is less than or equal to this. Let's say x0 is 2, right? Because 2 times 4 is 8. 2 to the fourth is 16. All right, so this is x0 is 2. And we know 7 is less than or equal to x to the fourth. Once again, I'll choose x0 is 2, because 2 to the fourth is 16. 7 is less than or equal to 16. Okay. Any questions so far? I just broke this up into different parts. And this is something I like to do in order to prove it. Okay. So then what do? I just take in this case, I just take the highest x0, right? And then I add them together because the sum, for example here, if A is less than B and C is less than D, less than or equal to, let's say, then A plus C has to be less than or equal to B plus D. That's not a D, that's a B. Right? So that means the sum of the left side has to be less than or equal to the sum of the right sides. So that means x to the fourth plus 9x cubed plus 4x plus 7 is less than or equal to x to the fourth plus x to the fourth plus x to the fourth plus x to the fourth. That's 4x to the fourth, where from what x0? X0 from x0 is, we take the max, 9, is basically saying x is greater than or equal to 9. Okay, so what do we have? We have our C, we have our starting x, which is 9. And yeah, does someone have a question? Sorry, I wanted to see if the window was open. Anyone have any questions? Is everyone okay? Any questions?
Hey, how you doing?
Got a question? I will take the silence as no questions. Is everyone okay with this example? Does anyone want to do? Oops, sorry. No questions? No questions? Okay. Does anyone have another question in mind that they have?
Can you do 4 to show that again?
Number 4?
Yeah.
Okay. So use the definition of f of x is big O of g of x to show that 2 to the x plus 17 is big O of 3 to the x. Okay, let's do this example real quick. So we want to show this. So let's split it again. 2 to the x is less than or equal to 3 to the x from x greater than or equal to 1, right? Because 2 to the first is 2, 3 to the first is 3, 2 is always less than or equal to 3, checks out. And now 17 17 is less than or equal to 3 to the x. For now, let's do x greater than or equal to. It can't be 1 because 17 isn't less than or equal to 3. It can't be 2 because 17 isn't less than or equal to 9. So we're going to do 3 because 17 is less than or equal to 3 cubed. 3 cubed is 27. 17 is in fact less than or equal to 727, right? So this is good, right? So you split it up, and now we take the sum. So 2 to the x plus 17 is less than or equal to 3 to the x plus 3 to the x, which is 2 times 3 to the x. For x greater than or equal to, let's just take the max, which is x of 1 and 3, which is 3. So this is our c. This is our k. Or x0. And depends on what your professor likes using. I know people using the textbook uses k. A lot of professors use k x0. But yeah. So that's why this is why 2 plus 17 is big O of 3 to the x. This is our proof. Everyone okay with that? All good, all good. Does anyone want me to go over big omega and big theta? Because correct me if I'm wrong, I believe. Sorry, what was that?
Yes.
Okay. Do they go over big omega and big theta? Okay, here. Okay. But f and g be functions of a set of integers. We say f of x is big theta of g of x if. Okay. They go over big omega. Okay. So we got this. So this is going to be big omega of g of x. This is basically the opposite of big O, and that we say that f of x is big omega of g of x if there exists constants c and k, such that f of x is always greater than or equal to c times g of x. Right, so once again, this is f of x. This is c times g of x. I should have used it in different colors. Pardon me. This is f of x. This is g of x. Right? We see that there's a gap. So this means this is big omega. Right? This is an upper bound. No. Yes. Yes, upper bound. What did I just do? Okay. Someone's hitting again. We good? Okay. This means f of x is always greater. And then you have big theta, which is basically saying you have both, right? F of x is big theta of g of x if f is big O of g of x and f of x is big omega of g of x. You usually see these in terms of it has to be the same polynomial. So you could prove that x squared plus 1 is big theta of, say, x squared, right? Because if I choose, in this case, I could prove for the big O direction, which is saying x squared plus 1 is big O of x squared, I just choose c as 2. And then our k is going to be 1. And then for the other direction, right? So x squared is big O of x squared plus 1. I just choose c as 1. And our k is also 1. Because x squared plus 1 is always going to be greater than x squared because of this extra 1. Right? So you'll usually see big theta used in on these only on big O. Oh, okay. So you're only having big O. That's fine. I'm just gonna go over these two really quickly because I don't really think big O is the only one that like really is important later on when you go into your CS careers. But these are still useful, right? So big O, you got this is big. No, sorry. Oop. No. Yeah. Big O, big omega goes both ways, and thus you have big theta. And small o, I believe, is just the limit as x approaches infinity of two functions is 1, I believe, but correct me if I'm wrong. So yeah, I feel like if anything, you should focus more on big O. Big omega and big theta they won't really show up because they're not that they're not important, they're not as used, especially when you go on to data structures and in 323 when you learn about runtimes of algorithms, you just won't really use big omega and big theta as much. So does anyone have any other questions about big O notation?
Can we go over number 5?
Number 5, that is a great question. X squared plus 1 over x plus 1 is big O of x. Okay. Damn, that's a doozy. So x squared plus 1 over x plus 1 . 22 and 24. Sure, we'll do those. You know, you show that this is big O of x. Okay. If, one second, if 1 is less than 2, 3 is less than 4. One second. 1 is less than 2. 2 is less than or equal to, not that, sorry. And 3 is less than or equal to 4. Seems fine to me. For this function, I think we have to use big O the rule. One second, let me see what the I just don't want to get it wrong. Mike, correct me if I'm wrong. There's no big O notation for division, right?
I think we can divide like both denominator and numerator by x. So and then the biggest term will left as x. So
We could, but that's like taking a limit, you know?
you don't need to, and then the biggest one will left x. So you can compare with that. That is what I'm thinking.
I was thinking if you have, because we know that the top. So x squared plus 1 is big O of x squared. That we know, because the highest term is x squared. And we know that x plus 1 is also big O of x. So that means this is our f, this is our g, f1, g1, f2, g2. It's gotta be a rule somewhere. F2, then f1, f2 of x is 0, g1, g2 of x.
Or what about you just divide it?
But is there, I think we could divide it, because then f1
Y-
is this, that means f1 over f2 is big O of g1 over g2. So let's just say that this is going to be 1 over x squared plus 1 over x plus 1. Technically, this is 1 over f1. And this is big O of 1 over x. Yeah, that's 1 over g1. So I think we could use it. We're good. We just multiply it. In this case, we just say then this means that x squared plus 1 over x plus 1 is big O of, someone say anything in the chat? K is 1, C is 3. You could probably use K and C. X squared plus 1. Or I see what you're doing. X squared over x plus 1 and 1 over x plus 1. Let's try this way first, and then let's do that way. x squared over x. This is then going to say that this is big O. X squared over x is just x. I think that's one way of proving it. The other way, I think that Jacob mentioned, we could split this into x squared over x plus 1. Are you going to say something? Someone going to say something? Right? 1 over x plus 1. This is, this part's always going to be less than or equal to x from x equals 1. So this is going to be x squared over x plus 1 is always less than or equal to x from x greater than or equal to 1. Because 1 squared over 1 plus 1 is 1/2. 1/2 is always less than or equal to x. Sounds good. And this part is going to be less than or equal to x from x0 being also 1. Because 1 over 1 plus 1 is, wait, no, 2 over 2 plus 1. No, this isn't good. No, sorry. I don't think we can do it this way. I think the safer way is using,
Oh, you just divide it. So like just like divide the polynomial division.
I don't want to do polynomial division. That's like calc. I didn't sign up for a calc review, Mike. It's 220. Oh, no. I think this is a better way with the two functions. Because we know that this is big O of this is big O of this. So f1 over f2 should be big O of g1 over g2, which is this. Or you subbed k into the function. That works too. That works too. You want to go over how you did it on the board? I let you guys use annotate. Can you do that? I don't think. I've seen people do it before. I'm not sure. Didn't mean to put you on the spot, but does that make sense? The person who asked the question? Who asked the question? Forgot. You don't have a mouse? Damn it. You do. You're able to type. I see it right here. Beautiful. Go for it. Well, who asked that question? Devindra, does that answer your question somewhat? Let's see what while Jacob does his work.
Yeah.
Okay. And let me move this to somewhere you could say. There you go. Keep on, keep on, keep on. Wonderful. Student participation is always appreciated, chat. Love to see it.
I have a question. Why are we comparing the numerator to big O of x squared?
Because let me just write it here because I don't want to. Because x squared plus 1 is big O of x squared. I don't think you can use another function for big O here. Because the highest term here is big O, is x squared. So you can, if you use this, it'll help with the calculation. Does that make sense?
Okay.
We want to find like the tightest bound. We could say this is like big O of x cubed, but it wouldn't really help us in that case. Done, you say. Mm-hmm. Mm-hmm. C of x is greater than or equal to 1, C of 1 is greater than or equal to 1, C is greater than or equal to 1, x squared plus 1, k is 1, 2 over 2, 1. Sure. If that works best for you, then I say. If it works, as long as you get a good bound and it works, then I say go for it. In that case. Just don't put something stupid as a bound. You don't want to do C as like a million. It doesn't really make sense. Tighter bound better. Okay. Thank you, Jacob. Thank you, Jacob, for that. Let's do 22 and 24 real quick before moving on to what's the next part? Induction and recursion. We'll do quick examples of those. Induction is my stuff. Jacob, if you could you clear your board clearly? Thank you so much. Okay, this is a classic question that you might get. For my 220, this is like an example of what I got. You have the functions, order them. Let's start ordering. So right off the bat, and we gotta look at anything polynomial or log is always gonna be in the front, and always gonna be the fastest. So if I'm not mistaken, log n cubed is gonna be. If I do make a mistake, please correct me, guys and girls, or everyone else and everyone else. Log n cubed is gonna be the fastest, right? And then we have n square root of n log n. I think there's a rule that log to any power is always going to be less than or equal to some square root. Okay. Or some polynomial. I think so. Any log to any power, say a, is always going to be less than or equal to even n to like 0.0001. Let's say this is 1,000. Logs are always less than polynomial. Okay, so log n cubed is going to be the fastest. Then comes this. And then we have to look at anything with the base n, right? So we have this n to 99th plus n to 98 and n to the 100. Let's compare the exponents. We see here 99 is the highest here and 100 is the highest here. So n to the 99th. Why did I write an m? N to the 99 plus n to the 98 will always be less than or equal to n to the 100th because their highest exponents are different. Then comes n to the 100. Okay. Any questions so far from the first four? First four, I believe, were pretty self-explanatory. Okay. No questions. So then after this, now we come to the bases. So this is going to be where the bases are of difference. And if it helps, what you could do is you could always log, right? So we're going to compare 1.5 to the n and 10 to the n. I think it's pretty obvious in this case, but if it isn't, you take a log of both sides, you get n times log of 1.5 compared to n times log of 10. Log of 10 is a higher constant, so this is going to be greater. So it's going to be 1.5 to the n and 10 to the n. Okay. Any questions so far? Whenever n's in the exponent, and say instead of just n, there was some function of n, then that's where like taking log becomes very useful. Okay. And lastly, this is our last option, but in general, n factorial is always sorry, one sec. Thank you for muting your mic. N factorial is always going to be fastest. So forget about n factorial squared. That's like horrible. If your algorithm runs n factorial squared runtime, yeah, you're not gonna stay in your job for long. But n factorial is always going to be the fastest. Not fastest, sorry, slowest. Guys, you gotta correct me when I say these mishaps. I'm not an English dude. But n factorial is always gonna be the worst runtime. Okay. It's not even close. Right? Even like you might be saying, oh, this is 10 to the n, this is like 10 n times. Well, this is like n factorial. This is if n is like a million. How many zeros are in a million? 6, right? Six zeros. Yeah. This is 10 a million times. But this is even if without the square, this is a million times 999,999 times etc. That is way greater than 10 to the n. Right? So n factorial is always going to be the slowest runtime. And that leads us to this question. Suppose you have two different algorithms for solving a problem. To solve a problem of size n, the first algorithm uses exactly n squared 2 to the n operations. And the second algorithm uses exactly n factorial operations. As n grows, which algorithm uses fewer operations? This is going to be the faster algorithm. Even though it seems large, compared to n factorial, it's nothing. Right? As n grows. So like say n is the population of Queens College, which I don't know, like say it's 10,000. The 10,000 factorial is going to be greater. It's already really much greater than n squared 2 to the n. Right? And then you take like higher n, like a million, 100 million, etc., which isn't really that high if you guys think about it. Right? So having n factorial operations is very slow, and it's always going to be the highest runtime. Okay. Is everyone okay with that? Any questions? Because I don't want to spend too much more time on this. We're going to have to move on to induction and recursion recurrence relations. Everyone okay with this? So more number, the slower it will run. What do you mean by the more number? Okay, do you guys ever see the function graph thingy? There's usually a graph showing the run times. There you go. Right, this is our typical. Like n factorial goes to a larger number. Yeah, if that's the way of thinking about it. Like n factorial is just way higher of a number. Right? As you increase n, the value of n factorial just shoots up, and doesn't even compare to something like 10 to the n. And a good way of showing that is like here. This is like how they usually show it with like the log graphs. You see here how even 2 to the n, which isn't too small, mind you. Right? That's like it ends a million, ends 1 million. That's a million twos multiplied by each other. That's a big number. That doesn't even come close to n factorial. Right? N factorial is always the worst runtime because it shoots up so quickly as n increases. Right? If ends a million here, this is well, like we thought a million twos was scary. Well, now there's like a whole bunch of numbers greater than 2. Like I think the last two numbers are 2 times 1. Everything before that is like 3, 4, 5, 6, 7, 8, up until a million. So that's much better, right? So never try to do a n factorial runtime. That's not good at all. Okay, so we're gonna move on to induction and recursion. Does anyone have any specific question that they want to go over? I love this. I love this analogy. If anyone here is ever interested in taking like a math class for fun, I know it's insane taking a math class for fun. Do take like mathematical problem solving, Math 205, I believe. It's super fun. And that's literally where I learned everything about induction. But does anyone have a specific inductive proof that they want to go over? Like the whole idea of induction is proving infinite things, right? Like proving something for a finite amount of cases. Sure, you just go through every case. But say I want to prove something for all natural numbers or for every positive integer. Well, you can't do it an infinite amount of times. That's why you have to use induction, right? Using the ladder analogy, right? The base case is I can go on to the ladder, and the inductive step is given on any step k, I can always go to step k plus 1, right? That's the whole idea of inductive proofs. So let's see if we could find one. Okay. Train stops the first station, so the second station, next station. Okay, I don't really think we need to go over 1 and 2. This is just the idea. This is just the idea of induction. If there's infinitely many stations, right, on a train route, and a train stops at the first station, so it's running, great. And if it stops at any station, it goes to the next station. So it'll go on every station, because if I'm on any station K, I go to station K plus 1. Right? So by using this, you can go on the infinite amount of stops. Because if I'm on any station, I always go to the next one, and the next one, and the next one. So even if there is an infinite amount of stops, hypothetically, as weird as that does sound, through induction, we just showed that you will go on every single stop. Okay, so that's the whole idea of induction, right? It's usually for infinite cases, and even not for infinite. Even if there's like, it's useful for like a lot of cases, because it's very powerful. Oh, and also I should say this: there's a difference between weakened. I don't really think they teach you this, but they taught it because this is induction is inherently like a mathematical thing. There's a difference between weak induction and strong induction, and I'm not sure whether your professor just put much focus into this. Weak induction is whenever you use one base case, right? So I use the base case, I have one base case, and I prove for any k, I can imply k plus 1, right? Strong induction, usually you have multiple base cases, and this is where you use for anything up until k, I could prove k plus 1. So there's a difference between these two. Strong induction, in general, they usually don't specify a difference because weak induction is like inherently a type of strong induction, but for many cases you don't really need to use strong induction to prove weak induction does fine. Just wanted to prove that out. Okay, so let's do 3 as a good inductive proof. Okay, so let P of n be the same in that 1 plus 1 squared plus 2 squared plus yada yada n squared is equal to n times n plus 1 times 2 plus, one second, let me write this out. This is equal to n times n plus 1 times 2n plus 1 over 6. Okay, for any positive integer n. So what's the base case? Well, the base case is 1. Is 1 equal to 1 squared equal to 1 times n plus 1, in this case is going to be 2. And 2 times 1 is 2 plus 1 is 3. 1 times 2 times 3 is 6. 6 over 6 is 1. Looks good. Show that P1 is true. That looks good. We just proved it. So what is the inductive hypothesis? So assuming for any k less than n, right, less than or equal to n, we want to prove that this implies k plus 1 is also true. Right? So we're assuming k is true. Right? So we assume k is true. Assuming it's true, we want to then prove that the next step is also true. Okay? So that's this and this, right? So now let's prove it. Is this 5.3? Yes. 5.3. I just like this example because this is like a good step-by-step proof of it. All right, so let's prove it. We know that we want to show that P of k implies P of k plus 1. Well, what's P of k plus 1? P of k plus 1 is, let me move down here, 1 plus 1 squared plus 2 squared plus dot 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 plus k squared plus k plus 1 squared. What's this whole part? This is just k. And remember, we know P of k is true. This is an example of like weaker induction. So what's P of k? P of k is k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. Right? This is going to be just simple math. It's going to be k times k plus 1 times 2k plus 1 plus 6k plus 1 squared over 6. I'm going to pull out a k plus 1 out of everything. So it's going to be, let's continue down here. K plus 1 times k times 2k plus 1 plus 6 times k plus 1 over 6. Oh my word, I can't draw a line straight. Bingo. So now the simplification part is k times k plus 2k plus 1 plus 6 times k plus 1. Should I distribute? Mike, what do you think? Okay,
So you just distribute. That's the only way.
use k 2k squared plus k plus 6k plus 6, right? So I'm gonna 7. This is equal to 2k squared plus, if anyone does have to leave early, which is perfectly understandable, it's a Saturday. Please, Mike, if you could put the feedback form. It's very important that we get feedback for these review sessions, especially since we're going to start planning them for next semester. So if you guys have your feedback, we're thinking about possibly maybe even expanding this. Maybe we're trying to rejig it. So two numbers I multiply to 12 and add to 7. 2 times, no, 4 times 3 is, yep, times 3. This is like this whole step right here. This is like the hardest induction is probably gonna get, because this is like the mathy portion of it. 3k plus 6. I'm gonna factor out 2k from both. This is gonna be 2 times k plus 2 plus 3 times k plus 2. Factor out k plus 2, you get k plus 2 times 2k plus 3. So this is going to be equal to k plus 1 times k plus 2 times 2k plus 3. This 2k plus 3, I'm just going to rewrite it. Let's rewrite it real quick. K plus 2 is the same thing as k plus 1 plus 1. So it's k plus 1 times k plus 1 plus 1. And 2 times k plus 3, that's the same thing as 2 times k plus 1 plus 1. And lo and behold, what do we get? We've just proved it. K plus 1 is going to be this. K plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. Proved. Quite easily done. Okay? And that's the whole idea of inductive proofs, right? And for strong induction, you just have to assume more. So yeah. Does anyone have any other questions? Any questions about this example? Any at all? Does anyone have another specific question that they want to do in particular? I see something in the chat. Strong induction, because my professor taught it. That would be okay. Let's do an example of strong. I'm trying to find a good space. Just blank. Oh, we can be right here. Okay. We have strong induction right here. Right. This is the whole difference. Like you're assuming way more base cases. So let's do a strong induction that I like. I believe you saw this, like with the stamps. This is basically saying any number we have greater than or equal to 12. I can write that number as a sum between 4 and 5. Any number of 4s plus any number of 5s. Okay? So this is going to use strong induction, and I'll show you guys why. So let's assume the base cases. Base cases. So 12 is 4 times 3 plus 5 times 0. Actually, let me type. I could type. Oh my word, that makes my life so much easier. 12 is equal to 4 times 3 plus 5 times 0. Right? 13 is equal to 4 times 2, 5 times 1. 14 is equal to 4 times 1 plus 5 times 2. 15 is equal to 4 times 0 plus 5 times 3. Right? I could go on for more, but I don't really think it's. I'm sorry, this is actually 5.2 now. Yeah, this was 5.1. I'm sorry, chat. The last section was 5.1. This is now 5.2. All right, I'm just gonna go over basic induction. I could go on, but I don't really think I need to go on because after this it just repeats. So 16 is 4 times 4, 5 times 0. 17 is 4 times 3, 5 times 1. Right, so I don't really think it's necessary. Now, what do we do here? We can now assume by strong induction, well, let's see what we would do if we had weak induction. By weak induction, we would have to prove K implies K plus 1. Now, this is possible with weak induction. I think a lot of you know Andrew Martin. He showed me how to do it with weak induction. It's not pretty. I don't like it. Rather, we could use strong induction to have something easier. Right? What can we use? Well, now we could use cases 12 up until K. And in general, let's look at this. Instead of 12, let's do 16 up until K. Right? Because that's everything after, including 12. And what I'm going to do is I'm going to use K minus 3. Right? I'm going to use K minus 3 to prove K plus 1. Okay? What I'm going to, does anyone have any questions so far? I'm using K minus 3 because K minus 3 is within this group, right? And I could use K minus 3 up until heck, I could use 15 in this case too, because 15 minus 3 is 12. That's one of our base cases that we proved, right? So now the idea is using K minus 3, I could prove K plus 1. Well, what's K minus 3? K minus 3, since we already know it's true, that's equal to 4 times sum Q plus 5 times sum L, right? Well, now I'm going to add 4 on both sides. Why? Because then that's going to give me K plus 1 is equal to 4 times Q plus 5 times L plus 4. I'm going to bring the 4s together. That's going to be 4Q plus 4 plus 5L. I'm going to factor out a 4 from this first portion. It's going to be 4 times Q plus 1 plus 5L. Well, Q plus 1, that could just be another number. So let's just name it M. 4M plus 5L. And there we go, we just proved it. K plus 1 is equal to 4 times some number plus 5 times some number. And that's the beauty of using strong induction, right? Like I said, you could use weak induction. You could just use K to prove K plus 1, but this is just much easier. You see that? And I think who asked that question? Franco. Do you see why this is a good case of strong induction? It's just way more powerful, right? Yep. Does anyone have any other questions? Any other questions at all? I'm gonna try to
Can you just summarize that one more time?
summarize this proof right here.
Yeah.
Okay. So the reason why we have this proof with strong induction is that with weak induction, we prove one base case. Scroll a bit. We prove one base case, and we use the notion that if I'm on any K, I can prove K plus 1, right? But that's useful. However, in some situations, we can't really use that. And even if we can use K to prove K plus 1, it's not really the prettiest to write or like to see. So the idea of strong induction is we use a lot more base cases to then prove that for assuming all of these are true, not just one thing, everything here is true, we could then prove K plus 1 is true, right? And in this case specifically, why that helps is we're assuming everything from 15 to K is true, right? Well, why can't we use K minus 3? Well, that would be useful here because K minus 3 is true for all of this. K minus 3 is in this, and it works. It's always true because the minimum K can be is 15, and 15 minus 3 is 12. We just showed 12 is true, right? This is why strong induction usually requires a bit more some more base cases. So we could use K minus 3 to imply K plus 1. Well, once we get that, it's just simple math, right? K minus 3, we know that's true. What does it mean being true? That means it's equal to 4 times some number plus 5 times some number, right? So let's add 4 on both sides. Once again, we add 4 on both sides. And what do we get? K minus 3 plus 4, well, that's K plus 1. And on the right side, that's 4 times some number plus 5 times some number plus 4. Well, the 4s can go together. If we take out a 4, we get 4 times Q plus 1 plus 5 times L. Q plus 1, well, that's just another number. A number plus 1 is just another number, right? It's still a constant. So what do we just show? K plus 1 is equal to 4 times some constant plus 5 times some constant, which we wanted to show for any n. Does that make sense? That's the whole idea of strong induction. It's more base cases, and thus you have more tools in the toolbox to use to prove anything. Okay? Everyone okay with strong induction? If it's the case, everyone's okay with it, I might move on to the next topic. All right, and like I said, if any of you are just as crazy as I am and you actually take a math class for fun, I do highly recommend taking mathematical problem solving with Elliott Gangram. It's super important, especially like the art of proving, especially in CS, is very underrated, and I think a lot more people should know how to do these proofs. All right, so 5.3 you say. Okay, recursive definitions and structural induction. Oh, so these current relations, recursive definitions. Do you have a specific question that you want to go over? Scroll down to the thing recurrent relation, recursive. Okay. F1, F2. So the whole idea of recurrence and recursive relations is that everything is built off a base case, which is like your very first case. And then it's just a formula that uses any case. You go to the next one. So I don't think we need to solve for this one. It's just the idea of solving these is pretty simple. You take the case, we know F0 is 1, and we want to prove any. So we know that this is going to equal f of n plus 1 is f of n plus 2. So f of 1 is f0 plus 2, which is 3. Let's write that. F of 1, I could type, I forget that. F of 1 is equal to f of 0 plus 2, which is 3. F of 2 is equal to f1 plus 2, which is 5. Right? And and they also ask us to find and a lot of times you'll be asked to find specific formulas for it. Right? So set of positive, odd positive, set of odd positive. What the hell is this? By this, do they mean like, what do they mean by this? Set of odd positive integers. Well, let's see. F of 1, the first one is going to be 1. So we could just say, okay, it be something like, let's write it down. F of 1, our base case, the smallest odd positive integer is 1. Why can't we just say f of n is equal to f of n minus, or in this case, f of n plus 1 is equal to f of n plus 2. Why can't I just say that? Right, because taking an odd number and adding 2 just gets us the next odd number. And same thing here. Whereas our f of 0 is 0, and f of n plus 1 is equal to f of n plus 2. I'm not gonna even bother doing B and C for both of these questions. I'll be so honest. You're not gonna get something like that on the exam. You're really not. Sorry, chat. It's been a long day. I don't want to sleep. I've been forced. Although I am getting paid for this, but I'm not doing B and C. You're not gonna get anything like that. You're not gonna be asked to do that. These aren't questions that you get. Something you're gonna get instead is like, given a recursive relation, give me like an explicit formula for it. All right, so given this, right? Give me an explicit formula for any n. That's something you're gonna. I don't know. Sometimes I feel like professors sometimes for some of the more questions, they just look at the questions, and sometimes the one that intrigues them the most, they just put that on the homework questions, trying to see how students would solve it. And like guinea pigs, which we are. But something you're most likely gonna get is, I'm gonna give you this formula, the recurrence formula, right? Give me an explicit formula for any n. Give me a specific what? Oh, I forgot I had that. Give me like a specific formula for n. This is saying f of n plus 1 is equal to 3 times f of n. Fine. What if n instead of 4 here? What if n is 400? Right? Well then, in order to find 400, I need 399. To find 399, I need 398. And you guys are starting to see the issue with that. I need to go all the way down up until the smallest case, the biggest case that I have, which in this case is f2. Well, not even that. I think f of 0 is the smallest, right? I don't want to do that. So rather, what I'm going to ask you to do, this sneaks into the idea of recurrence relations and explicit formulas, is given this, give me an explicit formula for any n that it gives me the exact value. All right, so I'm going to do one example here. We know that, well, here, let's do this one. Right, so this is f of 1. We're doing part A here in this case. F of 1 is f of 0 plus 2. Fine. F of 2 is f of 1 plus 2, which is equal to f of 0 plus 2 plus 2, which is 5. Is that visible for everyone? Hopefully it is. I'm trying to make some space. Wait me a quick second. Never mind, they found their car. Wonderful. So what I'm going to do next, f of 3 is f of 2 plus 2. What was f of 2? F of 2 is this. God, that's not f of 2. It's not that tenants form. Sorry, chat. It's this. 0 plus 2 plus 2 plus 2. Well, what is this? So what do we see this? We're starting to see the pattern, right? This is f of 0 plus 2 times 2 plus 5, right? This is going to be f of 0. Oh, sorry, this is not equal to 5. This is f of 0 plus 3 times 2 times 2 is equal to 7. Right? You starting to see that? 7. Is that visible? Is equal to 7. Right? And I continue it, but you're starting to see the pattern that for any n, if we want an explicit formula, that f of n is equal to f of 0 plus 2 times n, which in this case is going to be 1 plus 2 times n. So if I wanted f of 400, instead of finding the case 399, 398, etc., what I can do instead, f of 400 is then equal to 400 times 2 plus 1, which is 801. See that? And this is an example of what you're going to get most likely from this, right? If it's like an explicit formula, you're going to start seeing that this is one strategy that you could use to find, like, given this recurrence relation, give me an explicit formula. This is a good strategy that you could use, right? And most of the other examples, it's just the idea of substituting it back in and seeing if there's a pattern. If that pattern works, then stick with it. And then the whole idea, which you'll learn later on, is now that we have this formula, how do we prove it's right? That's where you use induction to prove that it's correct. Is everyone okay with that? Any questions? Any questions at all? I'm not gonna even bother doing this at the rest of these. It's not gonna get on here. All right. Given any sequence, give me a closed formula. That's just another example of it. A of n is 6n, right? So if you go backwards, it's kind of like, well, this is the pattern. How do I reverse engineer it? Let me find a question, because sometimes you're gonna have to use algorithms. Yep. No, not that. Does anyone have any other questions that they want to go over? Trying to find examples with the ignore the merge or everything that you're gonna learn in like 323. There's one with something Roth relation. Is everyone okay with that induction and recursion? Because if anything, I'm gonna move on to probability. My jam. Probability nerd that I am. Someone said something in the chat. 8.1. 8.1, they say. 11.1 for Jacob. We're gonna, after we go over probability, we're gonna go over into like trees and graphs. So if you have any probability questions, recurrence relations, disgusting. Before that, does anyone have any questions about probability? Discrete probability, Bayes theorem. I think someone did mention a Bayes theorem question, but depends on which. Yeah, because I believe there are like the 220. All the 220 sections are like in this one review. So Delaram, not Goldberg. Y'all had your final. I mean, if you're in Goldberg, I don't know why you're here. Kong, Caesar Ready. So it's like a general one. So does anyone want to go over probability? Anything probability? If not, we're gonna jump into recurrence relations and stuff. You all just did 7.4. What does that mean? Oh, expected value invariance. Does anyone have a specific question? The whole idea of like expected, and you learn much more about this in like Math 241, right? So like given a die, what's the expected value? Well, you take every possible value you could get and you times it by its probability and you sum it all up, right? Sorry. Hat checker problem. That is oddly specific, and I'm not sure what can you put a number on it? Right. So like let's go back going back on expected variance. What I like to do used to do, this is what I learned in 241. I cannot draw a straight line for my life. That's better. Right. What I like to do is given any x, any probability possible, we have its probability. Probability of x. Who is showing up now? Right. So in this case, x, when you roll a die, what are the values? 1 up until 6. What are their probabilities? All of them are 1/6. Right? So if I want to find the expected value, I do x times p of x. So this is going to be 1 times a sixth, which is a sixth, up until 6 times a sixth, which is 1. You see that? 1 times a sixth is 1/6. This is going to be 2/6, 3/6, 4/6, 5/6, 6/6. And then you sum them all up, and that's our expected. Right? In order to find the variance, what do? Is we multiply x again. So this is gonna be x squared, p of x. All right, so 1 times 1/6 is gonna be 1/6, up until 6 times 1, which is gonna be 6. You sum those up again. And how do we get variance? Variance is equal to e of x squared, so which is gonna be this sum. That's this. Minus e of x entire thing squared. So that's going to be this. Oopsie daisy. This value squared is this. And that difference is our variance. Right? And then the square root of variance is standard deviation. Right? So that's just like the lowdown of expected and variance. So if I ask you the expected value of a die, even though it looks weird that it's like 7.5, this just means that if you roll a die, you should get around 3.5, or equally likely to get a 3 or a 4. Right? These are just different ways of saying the same thing, so I wouldn't really worry about that. Example 6. New employee checks the hats of N people at the restaurant, forgetting to put claim checks numbers on the hats when a customer returns for the hats. Gives them back hats chosen and randomly hats. Hats are returned correctly. Oh. If x equals 1, correct hat, x 0, otherwise. Oh, this is basically like, this is an example of the probability. Like this introduces a key law, which I think is important. If you have any event, like in this case, we have n hats that can be chosen, right? If they're all chosen equally, that means the probability that any person gets their correct hat is 1 over n. Basically, you put your hand in and you take out a hat. If there's n hats, that means there's n possibilities. Right? So each hat being the probability of a hat being chosen correctly has to be 1 over n. And this goes back to kind of like the die problem, Whereas if we know that there's a finite amount of possibilities and all of them are equal likely, and the probability of each individual event happening is 1 over the total, right? So when you roll a die, there's 6 possible numbers. So if I ask you what's the probability that I roll a head, I'm stupid. That I roll a 6, not a head. I think a lot about coins. That I roll a 6, that means it has to be 1 over 6. 5, 1 over 6. 3, 1 over 6. 4, 1 over 6. All of them are 1 over 6. Right? And the second part that this hat checker thing includes is that the sum of everything has to be 1. So the sum of all possible probabilities in any experiment has to equal 1. So something has to happen. You put your hand in, you have to if someone asks for their hat and you put your hand in and you choose a hat, that hat has to be from someone. You can't just have a random hat that chooses in there. So if a person walks up to you in this situation, they have to have a 1 over n possibility of getting their hat. Right? There can't be a hat that doesn't have an owner, if that makes sense. This is also what this is saying. Does that make sense? Is everyone okay with that? I take longer breaks is because my voice is starting to hurt. Talking for an hour and 20 minutes takes a toll on a person. Uh, 8.1 is one of your major reading. Recurrence relations, my best friend. Oh, sweet God. Okay, so this is is this the third one? Is this the third hardest reading? Oh, it's not that difficult. It just seems annoying because of the formulas that are in it. Right? So what is it? The general formula? I'm just gonna find that one. Recurrence relations. I'm not gonna talk too much about these because you'll learn more about like the algorithms corresponding with them. Okay, this is a good one. Right? So you'll learn about the algorithms in 323. I'm not gonna put that much effort on them now. Well, let's go about solving them. Right? So linear homogeneous recurrence relation of degree k, right? So this is, once again, it should look familiar. For n, in order to find any term n, it's equal to something like this. This is basically saying some constant times the last term plus another constant times times the term before that, up until this constant times the first term or beginning term. And if we have an equation of that type, right, we could then have different ways of solving it. In this case, we have this first example, the degree 2 case, right? So if we have something like this, where a of n is equal to constant 1 times the last term plus constant 2, we did not do 8.2, just 8.1. Is this not 8.2? Oh, you didn't do this. See, that's where it gets confusing because you're in Kong, he doesn't do this. Whereas this is done in almost every, I'm just gonna quickly go over this. Then we're gonna go over 8.1. We'll backtrack. But basically the idea is this is how you solve. This is like one of the ways you can find the explicit formulas for it. Right? So then right here. So then the sequence solution, yada yada yada. If and only if a sub n is equal to alpha 1 times r1 of n plus alpha 2 times r2 of n, for n is this, where alpha 1 and alpha 2 are constants. Right? So by having this, we could then solve. Right? So if I'm given this recurrence relation, And I'm telling you, find me a specific formula for any n where a0 is 2 and a1 is 7. How would you do that? Right? This is one way. We use a theorem. We find the characteristic equation is this, r squared minus r plus minus 2 is 0. We get the roots, and then this using the theorem, we get that this is going to be the explicit equation. So now what do? We solve for alpha 1 and alpha 2. Well, how do we do that? We use our initial constants. Alpha 0 is 2, alpha 1 is 7, right? And what does it become? It becomes a sequence of linear equations. We get alpha 1 is 3, alpha 2 is minus 1, and thus the solution to the relation is this. So this is our now explicit formula for any n, and given this recurrent relation. And another example here is for Fibonacci numbers. It looks really weird, but this is just how it looks like, because this is the root. These are the roots of the equation. It looks very complicated. It's really not. These are just the roots, just quadratic formula. Right, then you use the systems of linear system equations. You solve for alpha 1 and alpha 2, and once again, there you go. So now, given any number, right, or if you guys know the Fibonacci sequence, 1, 0, 1, I think it's 1, 2, 3, 5, right? You take any number and you add the last two, right? This is 8, etc. So now we have an explicit formula that for any number n, so like once again, if I ask you what's f of 1 of 9, yeah, sure, 1,000, right? You're gonna have to need 999, 998, everything before. Well, now here, if I want f of 1,000, I just plug it into this equation, and I get it. Does that make sense? And that's technically what 8.1, yeah, 8.1. 8.1 is technically saying, right? Recurrent relation is kind of like, how do you, these are just like different algorithms of it. I wouldn't really pay much attention to the algorithms themselves. It's not, like dynamic programming. That's all that jazz you're gonna learn in 323. So I wouldn't worry too much about it, if that helps. And so given anything, how do I create it, right? Initial terms. How do I, given any two terms, how do I find the next one? Right, this is another example of it. Look at the questions. Induction, current relational permutations of a set of n numbers and elements. So it's just finding ways to show the current number by the last however many. All right, so constantly you coin the value 1, 2, 5, yada yada yada. Bills. Number of ways to pay a bill with n, in which order the coins and bills are paid matters. Not sure how I explain this. This isn't, cause not really, you're not gonna really get questions of how to create these. Although I don't know, for Kong, he bewilders me the way he teaches. Ro teaches graphs the entire semester and then introduces recurrent relations at the end. Boggles my mind. More than anything, you're gonna have to know how to do these types of equations, like how to solve them. That's more important in my opinion. Like creating these equations. And there's another one. There's another right here. Right? If there's like the same root, there's only one root, then you have this. Yeah. I don't know. He bewilders me. He does graphs the entire semester, ignores everything like induction, probability, and everything in between, and then says, "Oh, here are some readings. Read them. They might like most likely will be on the final." I'm like, "What is wrong with you, buddy?" No offense. There's a reason why he's a professor, but the way he teaches it just boggles my mind. So that's the most I'm gonna do for recurrence. For graphs and trees, I'm gonna implore Mike to take over for now while I go grab something to eat real quick because my throat is hurting. So yeah, Mike, are you there?
Oh
Feel
yeah, yeah. Yeah.
I'll stop sharing my screen and There you go. So all up to you. I'll be on the chat. I'm gonna go eat something real quick. I'll be right back. I'll be right back, guys.
Okay, so let's. All right, why he is eating, I'll be a little bit explain about some graph from trees. So yeah, where do you want to start? Start with tree or graph? Okay, 11.1. All right, so tree. So tree, it's a tree, yes. So tree is a graph, but it only has one starting node, which is we call it like a root. Right? In a tree, you see in a tree we have a root, leaf, tree like that, right? But in like tree, like when you have a tree, this is the root, right? These are the root, these are the leaf, and stuff like that. But in mathematical trees, it's like upside down. So your root will start in the first, and then you can have more than two children, right? So this is a root node, and this is, we call it children. So we can have like as many as children we can. It's not only two, because most of the students confused with the binary tree. But if it's just a tree, you can have like multiple children, right? So then if the children doesn't have, sorry, if a node doesn't have a children, we call it a leaf. So this guy, this guy, this guy, this guy, this guy, those we call leaf, because leaf doesn't have children. Right, this is the terminology. And then another terminology is like we have a root and we have only two children in each node. So we call it like a binary tree. Right, so this is a binary tree. This is just a tree. And then tree only goes from up to down. Okay, it only goes to one direction. It doesn't go to another direction. It is like if you took 212, if like you learn about like inheritance. So inheritance is basically like a tree. So it doesn't like go reverse order. It only go up to down. Yeah, this is a basically root. So this is a root node. Yep, so it's a root A, root C, it goes only one direction. So in here, the root is C. The other cannot be like a root. Oh, the root can be C, the root can be D, and so on and so forth, right? Let's see. Is there any problem you want to go over? Or is it just like yeah, so a tree with n vertices has n edges. So what is a vertices? So if you have like these, right? We have like this. So these dots, right? These nodes are called, we call it vertices. And these lines that connect to vertices are called edges. So we always have n-1 edges in every tree when there's n vertices. Okay. Then yeah. Is there any question you guys really want to go over? Or just a general? Okay. So let's look at number 1 and number 3. Okay. Let's look at number 1 first. So which are the tree? So we just need to find which one has a node, root node that can go to everything. Remember, it can be the children can be more than one. Right? So this is a tree, right? We can call this as a root. This is a root. We can call any node as a root. This is not a tree because here is like disconnected. And this can be tree. It overlap, but it doesn't matter. If this is a root node, we can go from one direction. Right? And this is not a tree. Because you see, we have a loop. Tree cannot have like a loop, like a cycle graph. This one, E can be a tree. Yep. So you can see this as a root now. Root can have like 6 children. This is good. This is tree. And this is not a tree because we have a cycle. In tree, we cannot have a cycle. Okay, great. All right. So, okay, let's take a look at number 3. So which vertex is the root? Okay, what do you guys think? Which one is the root? Answer in the chat. Oh, A, yes, correct. A is a root. So this is A. Which vertices are internal? These are more than one. So many. Can guys give me some answer?
BD.
Yeah, it can be B, D, C. All things that are not leaf or that are not root node. All of them in the middle. They are internal. They are internal vertices. So which vertices is a leaf? Yep. I don't think A is internal because A is a root. All right, L is a leaf. It's not an internal. Internal mean like any vertices that is other than the root or the leaf. It's like internal mean like inside, right? So inside mean inside the tree. Right? And you can imagine like you see a tree like outside. Where is the leaf? Leaf is the outermost part of the tree. So your leaf are you see leaf, when you see the graph like this, leaf are all outermost vertices that doesn't have any children. So there are so many things like E, L, M, N, G, O, P, S, U, I, R, K. Those are leaf. Right? Okay. And which vertices are children of J? Where is J? J is here. Okay. Can you guys answer which vertices are children of J? Q and F? Or Q and R? Yes, Q and R. These are the children of, yep, Q and R are the children of the J. All right, that is correct. Which vertex is the parent of H? H is here. C, correct. C is the parent of H.
Are S, T, and U also children of J?
No, they are not. We can call like grandchildren, or we can call like descendants. But like children is like you know, uh the immediate like one like connection. Like those are far, so they are like grandchildren.
Okay.
Yeah, descendants. All right, okay. So next question is, which vertices are sibling of O? Who's here? Which are the siblings? P, that is 1. And Yeah, sorry, yeah. Only P is a sibling. Right, here, look at this. What are the sibling of L? It's M and N. Right? It's like a siblings in our life too. Yeah, you have all like same parents, different children. Okay. What are the ancestors of M? What are the ancestors of M? B, A. It's not just B and A. Yeah, F, B, and A. F is also an ancestor. So it's like it's like in your life, like what is your ancestor, your parents, your grandparents, your grandparents. So there's like ancestors. What are the descendants of B? It's an easy one. Descendant of B. E, I. Yeah, this is L. So it's a E, L, M, and F. Yes. F is a parent and ancestor. Yes. So yeah. So the way we call it like ancestors or parent is like depending on like which perspective. For example, yeah. For example, if you say from N, F is our parent, and it also an ancestor. For example, H. This H is when you look at from the H, C is the parent, C is also an ancestor. So like parent is also ancestor. Yep, EF, LMN. So those are our descendants. Yep. When you see parent, and then ancestor are the same. Okay. Which question we want to go over? 5. Is the root tree and exercise 3 a full harmony tree? Okay, so these are names. So like we have some, I don't know if you guys go over like full tree, balanced tree. Did your professor go over a complete tree? If it is not go over, yeah, you are not responsible. So because like those you were learning like 313. So have you heard about like complete trees, something like that? Okay, I will take that as a no. 9.3. 9.3. Let's see. What's relation? Which problem do you want to go over? Let's see. Let me try. What? Represent each of these relation on 1, 2, 3 with a matrix. On 1, 1, 2, 1, 2, 3. Oh, okay. Who is your professor? I was just curious. Account. Yeah. Okay. Okay. So okay, this is like okay. I think this is like very similar to like a graph, like I think adjacency matrix. Yeah, adjacency matrix. It's like adjacency matrix. I think, not sure. So I think like you have a matrix. Tell me if I'm wrong because like I did not learn in 220. I learned in like another class. So let me know if this is wrong. So you have like a 1, 2, and 3 here, right? You have 1, 2, and 3 here. And you see a relation here, 1 to 1 and 1. So when you see relation, make us a 1. 1, 2. So 1, 2. So I think you need to start read to like here, left to right. So 1, 2. So it's like 1 here, 1, 3 is 1 here. And then I think all of them are like 0. I think this is like a matrix that represent the list. So it's like adjacency matrix and adjacency list. You will learn in the 313 and 323. Yeah. So next question is similar. Again, 1, 2, and 3. Right? We have 1, 2, and 3. Right, so 1, 2 is 1, 2 is 100. 2, 1 is 2, 1 is here. 2, 2 is here. And 3, 3 is here. And all of them are 0. Do you get the idea? Like what do you need to do? Right, so is that correct? Let's say relation is like this.
Sorry, what was it?
Let's say relation is like I think adjacency matrix, right?
Yeah, the relation start node, end node. So yeah, it looks 1, 1, 1. Which part is that?
Oh yeah, question 1.
Which part? 1, A looks good. B looks.
Right?
Is that for A or B?
That's B.
2, 2, 1, 2, 2. Yep, looks good.
Do you guys get the idea of like what does the relations mean? Okay. Okay, number 3. Okay. So yeah. It's not bad. Yeah, when you look at like number 3, it's like you just like convert from like this to this again. So it's like you just name like 1, 2, 3, 1, 2, and 3, and you make a array of like, let's say 1, comma 1, and then 1, comma 3, comma this is 2, comma 2, this is 3, comma 1, and this is 3, comma 3. Right, just convert, just like reverse the matrix to the list. It's like it's not even like a exercise, like a playing a game. Using convert. Yeah. Any question about this? Okay, any question you guys want to go over? $29? This 29? 20? Oh, 20, okay. Draw a direct graph representing each of the relation from its side 3. Oh, okay. Side 3. Okay, this is easy. So you have like a 1, 2, 3. We say 1, 2, 3 as a vertex. So 1, 2, and 3 is here. So right, you see 1 and 1. So 1 to 1. So it's like code itself. 1 to 3 is 1 2 3. So let's go this way. And then 2 to 2 again. This is like cycle stuff. And then 3 to 1 is like this. We go again here. And then 3 to 3. It's like this. Right. So based on the matrix, you can translate that into a director graph. You will see this in 313 and 323. This is like a baseline. It's like you introduce about the graph. So yeah, basically it's easy. So you just need to look at like a 1 to 1. 1 to 1 is like 1 from 2 1, and so on. Right, this is number question 20. 29. How can the dirty graph of a relation are on a finite set of user measures is symmetric? Ooh. I'm not sure. Is there any like a theory formula or something? Maybe if the matrix is asymmetric, the graph is also asymmetric. If the matrix is symmetric, maybe. Yeah, I'm not sure about answering this question. So yeah, you can answer like you can answer like general question. Like I think if you just need to write it down, just write it out like when you see a graph, convert to the matrix, and then you check if the matrix is a symmetric, or so if the matrix is like a symmetry or asymmetry. If it is asymmetry, it's wrong. It's not asymmetric. Maybe you can answer like that because like the question is like very general. So I think next thing you can do is like you can like draw a graph and then see you can like identify like asymmetry or symmetry from the graph. Got it? Also, don't forget to fill the feedback file. All right, can we go over number 10? Okay, how many non-zero entry does the matrix representing? How many non-zero entry does the matrix represent the relation R of A? So for the first 1,000 positive integers. Okay. Okay, so I think you just find a pattern and you just calculate like how many there. So this is like A need to be less than or equal to B. So it's like, let's say 1, 1. It's like 1, 2, right? And then 1, 3 up to 1,000. So this one has like, we have 1,000 relationship. All right, and then you can keep going like 2, we cannot have 2, 1, so it's 2, 2, and up to 2, 1,000. So which is like, we have like, here if we count with like 999. So now you see the pattern, right? So it's 1999, and it goes up to 1. So like 1999, blah blah blah. So it's like when you do like you can make a like arithmetic arithmetic series, right? So it's like 1,000 plus 999 plus and so on. So it's like there's a formula, right? I think it's like n minus 1 over n, I think. Over 2. And then you just plug in like 1,000 here, I think. And then you will get like how many are there? Right, Suleiman? It's like this is like a arithmetic series.
Which one? 10C, 10A?
Yeah.
Knowns your entry is a matrix representing. I think it's gonna be the upper triangular.
Yeah. So it's like 1,999 and so on.
One. It's gonna be only the upper triangular one,
Oh yeah, you can do like that too.
right? So it's gonna be I want to say not exactly n over 2, but not, I think 1,999 n factorial ones.
Yeah, and factorial, but like instead of multiplying, you just need to add.
Yeah.
So it's
Mhm.
like arithmetic series. So there's
Oh,
a
yeah, yeah,
formula.
So it's n times n plus 1.
N plus. Oh yeah, n plus
One
1
over
or n
2.
plus.
Yep.
Yeah, and then you plug in into the formula, you get the answer. Then next one, it's like the same thing, you just need to like write it down. So a equal to b plus 1. So if a is 1, b plus 1 is, let's say b is 1, so b plus 1 is 2. And then and so like 1, 2, 3 up to I think 1 comma 1,000. Right, this is plus, and then we need to think about minus too. So minus is like so 1 comma b cannot b if b is 1. I mean I don't think b can be 1 because like 1 minus 1 is 0. So b start from 2. So b need to start from 2. Let's say this is like a 0 here. B start from 2 is here. B is 2. It's 1 comma 1. That was 1 comma 2, 1 comma 3, and so on up to 1 comma 999. Right, this is just plus or minus. So and then we have like these thing like another 1,000 times. So a is like 1,000. So if you think like this as a column, right? We have like how many columns? Like 1,000. This is like 1,000. I think this is like a. Okay, we cannot have like 1,001. So like the first row is 999. The second row is 999. So it's like 999 times 2. But then if you get the answer, then I think it's just time another 1,000. Because we have like a has the 1,000 row. Okay, got it. Okay, I hope you understand. I think these questions are like, first you just need to write it down or put it in the matrix, write some number, figure out the patterns. Once you figure out the patterns, you will know how to count, because like I know you already took 120, Met 120, so it's like this is easier than Met 120, so it's just finding the pattern. Okay, I think just for time, because we also have like another review section at like 4:30, so I will stop here. But before I stop, let me show you where you can find the Learning Common website. I mean the recording, right? So Learning Common QC, and then you find website. This is our Learning Common website. And go to resource. When you go to resource, you see CSE and resource. CSE and resource, we have like for the recording here. Click the 220. You see, we have like attempt 2, something like that, and then we will put like in next line for the final one. So I think I did the earliest. I think it will be uploaded tomorrow morning. I think that will be the earliest time. You'll see in the page. So I'll put in the chat. All right. And yeah, so don't forget to fill out the feedback form so we can improve for the next semester. Okay, so yep, this is the end of the review.